So the first thing is the test on Friday. Exam 1 is Friday. And the topics are everything up through number 6 on strain and constitutive relationship. So that means that there aren't going to be any stress transformations. So I'd be happy to answer as many homework questions as you have, but when we go on to new material today, it'll be stress transformations, and that's not related to the test. Okay, any questions about the test? Yes. Oh, yeah. Mm-hmm. I mean, I could ask you to show. So, yeah, good question. So that's strain number 2. So, like, show what stress elements affect the XX strain, say. Okay, and the equation is EXX, YY, ZZ, gamma YZ, gamma XZ, gamma XY. Is equal to, and I'll write the form of this matrix out, so you don't have to remember this stuff, but 1 over E, negative nu over E, negative nu over E, 0, 0, 0, negative nu over E, 1 over E, negative nu over E, 0, 0, 0, negative nu over E, negative nu over E, 1 over E, 0, 0, 0, and then 0, 0, 0, 2 times the quantity 1 plus nu over E, 0, 0, and then that term just keeps shifting. And it's that multiplied by the Voigt stress. So that's sigma xx, yy, zz, yz, xz, xy. Okay, so if you're trying to use stress values to calculate the XX strain, the way this matrix multiplication works, EXX is equal to 1 over E sigma XX minus nu over E sigma YY minus nu over E sigma ZZ plus zeros. And so this shows you the dependence. The only stresses that matter for determining the X strain, the X normal strain, are the 3 normal stresses. And if I asked you something about, like, what about the XZ strain, shear strain? Well, this matrix equation says that that's equal to 2 times the quantity 1 plus nu over E times tau xz. And so there's only one stress that matters for the xz strain. So all that information is right here in the matrix equation. It's a single equation, but yeah, it's important that you know how to tease that information out of it. Because there are a lot of cases where it's just sort of overkill to go through the whole matrix equation. If you're just trying to figure out one deformation, like how much did this thing elongate when you applied one load to it, it's easier to just use the scalar equation. But if what you remember is the matrix equation, you need to know the relationship. Yes. Mm-hmm. Oh, 420. Okay. Yeah, exactly. I just like to put 420 in the syllabus. Yes.
Kind of a general question on problems like number 6 on the strain homework.
Mm-hmm.
Can we orient our coordinate system to have x-axis pointing in the direction of like deformation or
Let's see. I don't have those with.
just when we're finding Young's modulus?
Oh, okay.
Poisson,
Yeah.
like sigma xx
Yes.
over epsilon. Just to orient the axis.
Yes, I would always orient the x-axis in the parallel to the forces being applied. I mean, you could orient it a different way, but then the equations that I gave wouldn't exactly be right. It's all, Young's modulus has to be the stress along the loaded axis divided by the stress along the strain along the loaded axis. So I had it written as x, stress xx over strain xx, but that wouldn't be right unless your x-axis is parallel to the load. Yes. Sure. Do you have it with you or anybody? No, I don't know what that was. That was just sort of generally talking about. Yeah. I guess that is 2A. Yeah. Okay, so 2B. What's the algebraic relationship between the x direction normal strain? Oh, what's the algebraic relationship between the x direction normal strain and the stress values from part A? Oh, well, this really is 2B. Um, so 2A just asks which stress values it depends on. So really, technically 2A, the answer is just sigma xx, sigma yy, sigma zz. And then this is the form. I don't know why I broke it up into two things like that. I mean, really, both of them are answered by just coming up with the scalar equation for sigma xx or for epsilon xx. Any other questions about 2? Yes. Okay. Any other questions about 2 and before I go on? Okay. Okay. For 5C.
Your value in your stress tensor is -5. Good.
Okay. 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 So, the stress tensor, I guess, might as well just do it as a void stress because that's how we're going to use it to calculate the strains. XX is -5. There's no YY. ZZ is -20. Oh, we just did this in office hours, didn't we? Did we just do this one? And then xy is, well, there's no yz, there's no xz, and then xy is positive 10. This is all megapascals, so if you're going to do it in pascals, these all have to be times 10 to the 6. And then it should work out. Yes. So for C, now you would multiply this matrix by, so you'd have to come up with a compliance matrix, and you'd get that by just, using this form. I'm not going to write the whole thing again, but like just what I wrote just a minute ago. So this whole 6x6 matrix, and you'd substitute in values of 200 times 10 to the 9 pascals and a Poisson's ratio of 0.3. And now the units of Young's modulus match with the units of the stress. And so you can do the multiplication. And, you can just have your calculator do that and it'll give you some strain values. Anybody having trouble getting their calculator to do this? It might be a good idea to talk to me before Friday, because you'll have to do this on Friday and it'll save you some time if you get it figured out by then. If either of you guys are available for office hours right after this, just come to the tutoring center and I can straighten it out for you. Okay? Or if anybody. Any other homework questions? Yes. Okay. So number 6 is a tensile test. We're applying a force of 2,000 newtons. Um, the height is 0.15 meters. The width is 5 centimeters. That's this. And then the thickness is 5 millimeters, so 0.005 meters. And after deformation, it gives the new, so after the deformation, if we call this the height and this, nope. Call this one the width. Then after the deformation, the width is a little bit smaller, so 0.04, and then 1, 2, 3, 4 nines, and a 2. And the new length is a little bit bigger, so that's 0.15, and then 3 zeros and an 8. Let's see. Do we want to calculate Young's modulus and Poisson's ratio? And we'll use a coordinate system with the x-axis along the loaded axis. Y-axis, I'll do like that, and then, so this is x, this is y, and then x cross y has to be the z-axis, so the z-axis has to come out like this. Young's modulus is the stress in the loaded, the normal stress in the loaded direction divided by the normal strain in the loaded direction. And Poisson's ratio is negative offload strain, normal strain. So this can be YY or ZZ. We're going to use ZZ in this case because that's the values that are given. And divided by XX. And so to get these two values, we need sigma XX, epsilon XX, and epsilon ZZ. So sigma XX is equal to the total force divided by the cross-sectional area that resists it. Okay, so like when I, like back in my bodybuilding days, like you'd measure like how good am I at like resisting like deformation? Like think about what is it that, so like when I'm doing like lat pulls, you know, like what is it about the dimensions of my muscles that determines how strong I am? It's not the length, that doesn't have anything to do with it. It's the cross-sectional area like this, you know? And so it's that cross-sectional area that's that the load direction is perpendicular to. That's what we're talking about for the stress. So 2,000 newtons divided by the cross-sectional area, like that top area. So that's going to be 0.05 times 0.005. So that is 25 times. So I think that is I can't do that. Okay. 8 times 10 to the 6 pascals. And then epsilon XX is the deformed length along the x-axis, so 0.15, 1, 2, 3 zeros, and then an 8, minus the original, divided by the original. And what do you get for that? Okay. And then for the ZZ strain, so that's 0.04, then 4 nines, and then a 2, minus 0.05, divided by 0.05. And what do you get for that? Okay. And so now Young's modulus is 8 times 10 to the 6 pascals divided by 5.3 repeating times 10 to the negative 5. And what do you get for that? .5 times 10 to the 11 pascals. And Poisson's ratio is negative of another negative, negative 1.6 times 10 to the minus 6 divided by 5.3 repeating times 10 to the negative 5. And what do you get for that? 0.3? Ooh, I planned it that way. Sure. Now, is there any way that we could use this information to figure out? So I didn't give you a change in length in the other direction, that the change in the thickness. Is there any way we could calculate that? There is, or I wouldn't have asked. Because that Poisson's ratio is the same no matter which of those two offload axes you use, we know that 0.3 is also equal to sigma epsilon yy divided by 5.3 repeating times 10 to the minus 5. And so that says that epsilon yy is also equal to negative 1.6 times 10 to the minus 6. Okay. And that says that negative 1.6 times 10 to the minus 6 is equal to the deformed length of the thickness, so Lyy, minus the original thickness, 0.005, divided by the original thickness. Can someone do that algebra for me and tell me what Lyy is? It's definitely going to be, well, no, it's going to be positive, but it's going to have gotten smaller. And that's meters. Yeah, 2 zeros. So if we would have measured that direction, that's what we would have gotten. If it's isotropic, that has to be the case. And then that's it. And then you can use those values in the compliance matrix and then figure out the strains if you know the stresses at a point. Any other homework questions? It depends, like the kind of questions I would ask have pretty different lengths. So I mean, I'm gonna try to make it 35 to 40 minutes for most people, but the number of questions could vary a bit. Okay. So now going back to stress transformations. So last time I introduced the idea of a rotation matrix. And I'm going to call the rotation matrix Q. Once I knew what that Q stood for, but I can't really think of it right now, but there's a reason that we use Q. And let's say that we're trying to do, if you know vector components expressed in coordinate system A, and want the components in coordinate system B, the columns of Q are the axes of A expressed in B. Okay, so I always just remember that as like the order is A, B, A, B, if you say it that way. But this isn't the way that we're going to calculate this. That's the general, that's always true for a rotation matrix. But we're going to do rotation matrices that are sort of simpler rotations. And then let me finish this. So if you have, so your vector u in the B coordinate system, I'll write it as like expressed in B is equal to Q times U expressed in A. So that's the idea. We will do it. So our matrices in this class, so one, first, if you're rotating the original coordinate system, an angle of, excuse me, an angle of theta about the x-axis to get the new coordinate system. Then this matrix Q is equal to the matrix 1, 0, 0, 0, cosine theta, sine theta, negative sine theta, cosine theta. So what are we talking about there? So if we have, that rotation is, can I draw this? So maybe. Yes, thank you. Well, let's do a coordinate system like, so for example, let's say theta is equal to positive 90 degrees. That'll make it easier for me to draw this. And let's say we start out with a coordinate system like this with the x-axis to the right and the y-axis up. And then after the transformation, if we rotate positive 90 degrees about the x-axis, according to the right-hand rule, the x-axis is still going to be in the same direction. What direction will the y-axis be? Towards us, yep. So it starts out with this, the z-axis. Now the one coming out towards us is the y-axis. And which way will the z-axis be? Down, exactly. Okay, so right-hand rule. So put your thumb in the direction of the x-axis, because this is positive. If it was negative, you'd put your thumb in the negative x direction, and then just rotate this whole thing 90 degrees about, in the direction your fingers are going. Okay, so what this says is if you had a vector expressed in this coordinate system that we're used to, and you wanted to know what the components were in this coordinate system, you'd fill these in with a positive 90 degrees, multiply the vector in this coordinate system by that matrix, and you get the new components. You don't believe me, do you? Okay, let's see. Okay, so let's say so Q in this case is 1, 0, 0, then 0. What's cosine of 90? 0. What's sine of 90? 1, 0, negative sine of 90, cosine of 90. And so multiply that by, so now let's say that we have a, so let's do this with a vector that is okay, so let's say that's at 45 degrees, 45-degree angle. Let's say that that vector in our original coordinate system is 1, 1, 0. Okay, so now 1, 0, 0, 0, 0, 1, 0, negative 1, 0 times, well, let's say it's 2, 2, 0. It doesn't have to be all ones or anything. So what do we expect this to come out before we do that multiplication? If this works, what would it have to be in this coordinate system? What would that vector, so just move that vector over here, what would the components be? Positive 2x, 0y, negative 2z. Okay, do the multiplication and you get 2, 0, negative 2. Hold on, I'm drawing. Okay, what? That's just how surprised this guy is. Yeah. Did someone have a question? You don't rotate the vector. You just, the vector lives like, so all of this is just, think of it as like, this is the way that the math is just us describing this vector. The vector lives in that direction and we don't affect that. Okay, so the question is, a vector in that direction, what are its components in this coordinate system? Now that same vector living in that direction, what are its components over here? Yes. I just made it up. That's what I said that this was, you know. I just picked like an easy vector to work with. But so the question now is like, what are the components of that vector there? Okay, this is our vector u. This is our vector u. Because positive z is, yeah, right, exactly. Exactly. So this is u in the original, and this is u in the new. Okay, let me do the other two. I'm not going to do examples with the other two, but so second, what if you rotate an angle theta? So rotate the original coordinate system, an angle of theta about the y-axis. Well, maybe you'd recognize that there's going to be sort of a pattern here. when we were rotating about x, we had a 1 in the x spot and zeros, and then we had cosine, sine, negative sine, cosine. It's going to be similar for y, but remember y always has to be the strange one. It always has to be a little different. And so the rotation matrix for y is, so it does start out with a 1 in the YY spot and zeros along the row and column from there. And it does have cosine theta there. But now it has negative sine theta, positive sine theta down here, and cosine here. Almost the same pattern, but just a little different, the way y is usually a little bit different. And then third, if you're rotating the original coordinate system, an angle theta about the z-axis, now we go back to that pattern that we had for x. The rotation matrix is, so there's a 1 over here, and zeros along the row and along the column, and then cosine theta, positive sine theta, negative sine theta, cosine theta. Mhm. This works for anything that's a vector, but it's just a way to express, the components in some coordinate system, and you want the components in another coordinate system. Okay, so I'm going to do an example that to sort of show you an application of this. Okay, and there's a million applications. It comes really naturally in dynamics because you're usually measuring something in a coordinate system that's spinning around, and you need to re-express it in a coordinate system that's like fixed to the ground or something. But okay, let's say like you did these problems in physics 1, where you have an object on like a ramp. Let's say this angle is 30 degrees. And in order to calculate the friction and the normal force, you did this calculation in this coordinate system, right? And to do that, you had to do some trigonometry to figure out what the components are, right? Here's another way to think about it. So what's let's say, so if the mass is, well, let's just call it m. Okay, what's the weight force in that rotated coordinate system? Well, in this coordinate system, we know what, it's, you can immediately tell what the weight force is. Weight force, call it mg, is equal to 0, negative mg, 0, right? So now let's think of it as what we're doing is we know what that vector is in this usual coordinate system, and we want to do a coordinate system transformation from this into that rotated one. So Um, we'll start out with this as the original coordinate system. And our rotation will be, yes. Okay. So what kind of rotation does it take to go from this original one to this rotated one? Like what axis are we rotating around? What's the angle? What's the sine? Yes. Positive 30 about z. That's exactly right. Because the z-axis, x cross y is z. Okay. So the z-axis is this way. And if we're trying to tip this one up like this, so right-hand rule says that's in the positive z direction. The angle is positive 30. So theta is positive 30 degrees about z. And so q is cosine of 30. Yeah, that's right. Cosine of 30, sine of 30, 0. Negative sine of 30, cosine 30, 0. 0, 0, 1. We could do that numerically. That's like 0.866, 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1. And now we just multiply that rotation matrix by our vector in our original coordinate system. And so 0.866, 0.50, negative 0.5, 0.866, 0, 0, 0, 1 times 0, negative mg, 0. And we get negative 0.5 mg for the x component, negative 0.866 mg for the y component, and 0 for the z component. And that's the same thing you got doing the trigonometry. When you do that trigonometry, you're just sort of by hand, you're doing that coordinate system transformation. If you're doing everything by hand, this way of doing it is a ridiculous way to do it. It's so much slower, right, than just thinking about the triangle. But if you have this programmed into your calculator or you have MATLAB or something, once you get used to thinking of things as a coordinate system transformation, this is going to be like instant, you know? You just think like, oh, start with a coordinate system like this, pop it like that. That's a blup, 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 done. And you don't have to think, which is ideal. Yes. Mm-hmm. Yeah, you have to do it in order. And so you have to be a little careful because now, like say that you wanted to rotate, let's see, say that you wanted to first do a rotation about the x-axis and then a rotation about the y-axis. When you do your rotation about the x-axis, now you're in this position. And now if you, right after that, do a rotation about the y-axis, it's going to rotate about your new y-axis. Okay, so you have to, it takes a little bit of thinking. You can do it with some inverses and stuff, but yeah, you can. Any other questions about that right now? Okay. So these rotation matrices can also be used to transform any kind of tensor from one coordinate system to another. So if Q is the rotation matrix that goes from the original coordinate system to the new coordinate system, then the stress tensor in the new coordinate system is equal to rotation matrix times the stress tensor in the old coordinate system times the transpose of the rotation matrix. So you need to multiply, you need to left multiply by the rotation matrix and right multiply by the transpose. And the basic way that works is what you're doing. So loosely, just sort of intuitively, one rotation matrix rotates the faces of the stress cube and one re-expresses attractions in the new coordinate system. One thing that's worth keeping in mind, notice, I don't know if notice is the right word here. Remember that a rotation matrices are called orthogonal matrices. Which means that the columns of the matrix are all perpendicular to each other, if you think of them as vectors. And in an orthogonal matrix, so and therefore Q inverse is Q transpose. So whenever I use the transpose of a rotation matrix, it's really just an easy way of doing an inverse for that particular matrix. Any questions? Okay, well, let's stop there. We'll do the test on Friday, and then Monday, we'll get back into this and do some examples and stuff. Just the problems.